Okay, I think we better get this session started. This is our special SE named lecture, and I'll now hand over to Helen Glaves. Hand over to Ruth, who's the president of SE.
Hi all. I'm hoping that a few more people will wander in. If they didn't see Leslie's note earlier, they may take a while to get here because it's a big building. But in any case, welcome to this year's Leptoukh lecture. But first, Shelley Stahl from AGU's Data, you're director of data, right? All right. There's an actual director of data. Wow. Has a couple of words that she needs to say to our community. So take it away, Shelley.
Thank you, Ruth. So I am Shelley Stahl. I am the Director of Data Programs, and I would like to do this very briefly, but I need Aaron Robinson to please come up to the stage. So as Aaron is coming, and I did move to the middle on purpose, so I would like to read you a statement from AGU and SE. On behalf of the team at AGU and SE, I want to thank you, Aaron, for your incredible contribution to the informatics community. Through your work at ESIP, you helped to build the relationships necessary for our informatics community to be so effective. More specifically, you have been instrumental in the success of the growth and value of the AGU Data Fair and now the Data Help Desk. Your significant contributions to the Enabling Fair Data Project as a member of the steering committee have been instrumental in our current momentum. And lastly, as the chair of the AGU Data Management Advisory Board, you helped shape my work at AGU in ways that make my contributions more valuable. Thank you.
Here's your stuff, so more pictures. Thanks, guys. Okay. Thank you, guys.
And now, one more. Leslie Wyborn, come sit next to me. Yep, you. Right here. So Leslie, on behalf of the team at AGU and SE, I want to thank you for your incredible contribution to the informatics community. Your work on this and previous years' fall meeting SE programs has set new standards for program design and member engagement. You're going to make me cry. Your work connecting the informatics communities in Australia, the UK, Europe, and other countries with efforts to improve our infrastructure and standards is exemplary. Thank you to the National Computational Infrastructure, are you out there? And ANS, the Australian National Data Service, and AuScope for their support of your work. For AGU, I want to thank you for your continued contribution as a member of the AGU Data Management Advisory Board and the extraordinary work you have done at the Enabling Fair Data Project to connect the many international communities involved. Your work has made a significant difference in the quality of the AGU Fall Meeting program and the furtherance of the goals of the informatics community.
Thank you so much. I'll frame the photo.
And without further ado, I'd like to welcome Helen Glaves, the lead of our SE's Honors Committee, to give the introduction to our Leptoukh lecture.
Thank you, Ruth. Okay, good afternoon, ladies and gentlemen.
So the Leptoukh Lecture is an award made for an outstanding contribution by an individual to Earth and space science informatics. It is named in honour of the late Greg Leptoukh, who was both an Earth scientist and an active member of the informatics community, having been involved with many projects dealing with data quality and provenance. This lecture is organised to highlight the role of informatics across the earth sciences, as well as the accomplishments of individual scientists. It aims to raise awareness of the often overlooked computational and data advances that enable breakthroughs in domain science, as well as fostering exceptional individuals to make continued contributions in informatics and data science. At this point, I would like to introduce this year's Leptoukh lecturer, who is Professor Kirk Martinez. Professor Martinez is a professor of electronics and computer science at the University of Southampton in the UK. He has a BSc in physics from the University of Reading and has a PhD in image processing from electronic systems engineering at the University of Essex. Professor Martinez is recognized as one of the world leaders in both the theoretical aspects and real-world applications of environmental sensor networks and informatics. He began his research in the emerging field of environmental sensor networks in the early 2000s and developed the first ever wireless system to monitor subglacial processes. These environments are some of the most inaccessible on the Earth, but they are key to our understanding of how glaciers move and thus how they respond to climate change. Professor Martinez has subsequently gone on to develop the first Internet of Things system for sensing the environment in remote locations such as Greenland and Iceland, as well as the Cairngorm Mountains in Scotland. He has written numerous papers on both the theoretical aspects of wireless networks and research in glaciology, so he truly is an all-rounder. But when I was researching this introduction, I was actually most interested to discover that Kirk Martinez has also contributed to the public understanding of science in a very unusual and innovative manner, having led a team at the University of Southampton that created Erica, the cyber rhino. Erica was created as part of a citywide art installation in Kirk's hometown of Southampton, and it was one of those painted rhinos that you see around, or animals that you see around the streets. But what was unique about Erica is that she was actually web-enabled, so she had all sorts of state-of-the-art technologies installed that allowed her to interact with the public in various manners. With that, it is my honor and pleasure to introduce Professor Kirk Martinez, who will deliver this year's Leptoukh lecture, which is entitled Earth Sensing from Ice to the Internet of Things. So without further ado.
Thank you for that kind introduction. I hope this microphone's good. Yes, so SE has come a long, long way since, is that loud enough, I think? Yeah? It's one of these, I'm not going to go down to the microphone the whole time. I'm going to go there. Change your environment. That's the thing about primates, isn't it? Okay, so SE has come a long way since Jane and I ran the very first teaser session called Environmental Sensor Networks in 2004 as a way of actually bringing this subject into the AGU and bringing together all the disparate people from all over the AGU who were dependent on technology for their data. And we have, over the years, managed to keep going with our research in this area and bring more and more people into SE as well. So it's very exciting to be here and tell you a little bit about making data. So we all know that data is extremely valuable to our science, and sometimes it's a necessary thing for things like hazard monitoring. But not many people really talk about how they've created the data using new technologies. And what we've concentrated on is doing some basic earth science with some fundamental technology development and creation of new technologies, testing of new technologies. So I'm going to tell you a little bit about those. So environmental sensor networks are actually, put simply, just a bunch of sensors somewhere which talk to each other so that they communicate their data back to us in some efficient manner, not using too much battery power. And there are many, many papers written on this. At one point, the sensor networks community were producing 30,000 papers per year. So you can imagine that every minute aspect of the fundamentals of computer science and algorithm development have been looked at. But in doing that, very few people actually went out and tried some of these things in the wild to produce new Earth science data. So sensor networks actually are quite a complex topic. Obviously, the sensors themselves are constantly evolving and growing so that we now have things like biosensors, lower cost carbon dioxide sensors, and so on. But when you put these things together, you soon learn that all the other issues like reliability, it's pointless having new tech out there in the wild if it's not going to be reliable. The power supplies have to be very smart, otherwise you're constantly changing your batteries, et cetera, et cetera. And so the topics are actually too far and wide for me to cover. I'll touch on a few that we've worked on just to give you a taster. So in the GlaxWeb project, we actually worked on the tough project of what is the fundamental glaciology underneath the ice. So putting sensors underneath the ice primarily to see where the contact surface was, what the physics was under there. And obviously that's a nice, good challenge for me to produce systems that would reliably get data out from the glacier and back home to a server. So in doing that, we did seriously develop our own custom electronics, protocols for the networks, even radios, and generated lots of data, which was the main aim was really to generate lots of data. So in these studies, we started off in Norway, in the largest ice cap in mainland Europe, on a glacier called Brehen. But as you'll see, we had a few problems with that one due to melting. We actually then moved to Iceland and carried on our studies there. And in the later studies, I'll show you that we're doing in a subarctic plateau in the Cairngorm Mountains of Scotland. So when we first chose Brehen in Norway, we did so because it was a famous glacier for being large. It surged forwards, very accessible. Victorians used to take horse and carts up there. And so it was quite an easy place to work on. You could follow the tours of poor tourists up and do drilling and do whatever you like there. But with melting, and this, don't forget, is coming from a massive ice cap, by 2007, we could not work on the area anymore. And famously, the BBC came out to film us doing some research, and they just ended up filming us taking our equipment out of the lake, which is highly embarrassing. And now if you look at this on Flickr, so people who go out there and take photographs, you see that it looks like this. So basically, thousands of tons of ice have gone and possibly may never come back. So that's one of the reasons we moved to Iceland. So what do people actually use currently to study glaciers? Well, they used wired sensors. So you get a logger, you drill holes into the ice using these jet wash type hot water drills, and you wire the instruments down to where you need them, and then walk away, and then come back to download your data from the logger. So that's obviously not a very efficient way of making sure your system survived the stresses and strains of the holes closing and all the rest of it. And also, with one logger and lots of wires, you can only really cover small areas, so your spatial coverage is a bit limited. So what we did was we combined the traditional techniques of sampling, drilling, ground-penetrating radar, etc., GPS, motion studies, with the new sensors that we placed inside the ice. So the overall system had to be worked out. How do you get data from inside the ice, from these things we're going to put inside, out to our servers back in the UK? And we worked out eventually that you need a very low frequency, quite powerful radio inside the ice, which talks to a surface station. And then you can use some other techniques. We actually used high power Wi-Fi in many of the cases, or long range modems, to actually feed the data back out. But by the end of the project, we had quite a diverse mixture of things on the ice. For example, geophone nodes, which were measuring shocks to detect ice shocks. And we had a variety of several generations of these subglacial probes that were not necessarily compatible with each other. So these probes were very, very custom. Eventually, we had quite a good platform for these, a small circuit board, lithium thionyl chloride batteries that would survive the cold, lots of sensors, temperature, pressure, strain, conductivity, electrical resistance, accelerometers so we could measure the tilt of the things. So a large group of sensors, which some of them have never been tried before. So this led us to be able to, for example, see the motion of clasts under the ice in detail for the first time. So these things would be sealed up in this polyester case and placed into the system, into the ice system. So here is, I won't bore you with the gory electronics, but needless to say, adding a lot of sensors to a small microcontroller involves quite a lot of development work to get these small boards made. On the surface, that turns out to be even just as harsh. We actually had a Linux-based system with other things, for example, MET measurements, GPS measurements for ice flow, a variety of other sensors, but its primary task was to get the data safely home. So it would stash the data away on a memory card, but it would also try to push the data out through Wi-Fi links, or if the Wi-Fi didn't work, it would use telephone links. So it's quite a complicated system, but we designed this to survive through the winter on a massive Peli case full of lead-acid batteries. And even in October, you can see it was actually very harsh in Iceland, for example. The snow would eventually cover the solar panel, and then the system would realize that it was in ice and snow, and it wasn't generating any more power, and slow down its behavior in order to survive, to keep generating that new data that we wanted. So the use of Linux is quite common in these systems, but we obviously couldn't have a small computer running 24/7. It would just use all the batteries. So we had to generate a completely new system which woke up the Linux system, which then ran quite friendly Python scripts, for example, to deal with the GPS units and talk to the probes and so on. And these were actually, this is probably about version 6 or 7 of this type of design. And you would box them all up in some nice way with the GPS units and solar chargers and batteries and all the rest of it, and teach people to be very, very careful with the connectors, etc., to make this thing survive. One thing we learned at the AGU, so you can learn things just going to the exhibitions, was how the professionals do these things. And so we soon learned that we should just use what the professional manufacturers use on their very robust systems, for example, for all these big connectors. In fact, this system, the student sat on it in his bath in order to check that it was really, truly waterproof. There's dedication for you. I didn't ask him the temperature of the bath. So we then had a friendly Icelander running a cafe tour company on the top of the mountain let us install various antennas and systems so that we could use his hut essentially as a router to get the data from all these various antennas talking down to the ice, talking 16 kilometers down. That view there is sort of the ice, all the way to this little farm here where the farmer's network would then link the data straight into our cloud system. So you can imagine that by the end of many years of this, you have quite a sophisticated algorithm and rerouting, and it begins to look like a very complex system to debug, but it behaves in a very reliable manner, but very bespoke. There would only be 2 or 3 people in the world who would understand what was happening in your system. So here is a probe being dropped down a hole. If the hole was full of water, you could literally drop it down. And in this video, you can see it's obviously a bit juddery for a minute. But you can see the probe there traveling down the little ice hole, never to be seen again. And that's actually another thing about this research is if you're going to make sure your system is 100% okay, not that there's one more bug, one more feature you would like to add, and you're going to drop it down a hole, it really does concentrate the mind of the team. And luckily, in the end, we were getting years of data. We got 5 years of continuous data from these systems. And 5 years of continuous data is fairly rare in the subglacial environment. So when you start to put the data together with the strain, the new values of the case strain, the meteorological conditions, the GPS velocities, you start to see things like in the spring, it actually starts in January for the glacier. By February, spring is really truly there and things are starting to wake up. you start to see really long-term changes which are fundamental to our understanding of how glaciers change and move and melt and so on. So by the end of it, as I say, we had quite a heterogeneous mixture of systems, from webcams, some Wi-Fi systems running IPv6, different frequency radios. It's quite a complex system to make it work. And it was very bespoke, so it used like the minimum energy that you could possibly make this system to use. However, as earth science people, you don't really want to have to do this kind of level of technology to integrate some things. You'd ideally want to be able to buy a GPS unit from one company, some rain things from another company, put them together with some kind of magical network stuff, and it would all just work without needing 3 PhD students like I do. And that is the philosophy of the Internet of Things. So when you buy your internet-connected fridge, toaster, slippers, whatever it happens to be, you're relying on them being internet-connected, web-connected in some easy way. And luckily, of course, in a home environment, you're usually talking about Wi-Fi connected devices. And so you get medical devices, you get even door locks, plant devices, the dreaded light bulbs, et cetera, et cetera. Many things which are just instantly usable. And this is what we don't really have in the earth science sensing community. Nothing's particularly interoperable. Having said that, a big battle in the Internet of Things at the moment is making things interoperable and not being locked down to one manufacturer's stream of product standards. However, if we stick to the protocols of let's use internet protocols, let's use web protocols, let's go for interoperability and open source interoperability, a bit like we do with our data standards, then hopefully we can bring a kind of new way of developing to Earth sensing. So we got some funding to do this project we called mountain sensing, and we moved to Scotland. And the idea was to use a very large area again, so a typical area. And we had 2 or 3 use cases, measuring the streams, measuring the motion of the, it's basically almost permafrost up there. It's a high, semi-alpine environment. So we actually chose this as a test for using internet protocol everywhere and using web-based standards everywhere. Sorry, that is actually the view from the valley. So this is a 3-kilometer view up to this 1,000-meter mountain, and behind there are all sorts of nice, interesting study areas, hydrology, peat, etc. So on a map, you can see the kind of distances involved, which are fairly typical. So you've got a 3-kilometer jump to get to your study site, and your devices might be 500 meters, 1,000 meters apart. So basically, wherever people wanted to place their sensors, that would be the network. And then we'd have to design around that. And what we did is we built everything on a standard. So we used a standard scientific frequency, which is 915 in the US or 868 in Europe. So it's a lower frequency, so it's actually got quite a good range. And you can buy a variety of radios that work in that range that are interoperable. And they're interoperable partly because of this IEEE standard that lets the packets be interoperable. But then on top of that, we actually used IP version 6. So IPv6, the cool thing about it is all your devices get their own unique, globally unique internet address. This means that you can talk to them from your desk, as you would expect to talk to a web server somewhere in the world. Then we used a thing called Ripple, RPL, which is now a standard for mesh networking them. If you install Ripple, they will just automatically mesh network together, and they'll hop the data between each other in a reasonably sensible manner. And then we're only using UDP, so we're using the very short packets with no dedicated connection. So we're not using TCP, but this is getting a bit networky. You can ask me tomorrow at the poster if you want more details. A key enabler to a lot of this is not using HTTP, not using web protocols. So you want to use something standard, but as I'll explain, web is too heavy, it's too ASCII, it's too old in a sense. So we're using this thing called CoAP. And CoAP is like a binary version of HTTP protocols, so you can do gets and puts and posts and deletes even. So this is what our network looked like. Basically, you turn everything on, the Ripple protocol meshes them all up, And this is the building at the bottom of the valley that has an internet connection. Basically, the long link to one node seemed to be very, very important that it stayed up. So this node had no sensors. It just ran code that did nothing but root. So you just turn it on, and it helps that basic single point of failure to operate continuously. Now, over here, you have these nodes which are small nodes with different sensors on. For example, one might be doing temperature profiles, one might be doing stream, water depths, etc. And we arranged it so that if you plug in some different sensors and just link it into the network, for example, something that sends an array of temperatures, an array of accelerometer readings, would just send those readings out, and the readings would be in a standard format so that by the time they get to the database on the server, they're just unpacked. You know what all the values are. It's a bit like using XML, but not really. And so we actually had two nodes. This Peach node over here actually had some sensors on it. And one over here tended to be a single point of failure as well. So what happens is a little Python program, actually a Java program, mysteriously in this case, on this tiny micro PC in their shed in the farm, requests data from each node in turn, so that we could really control it. Another mode we did was you just let the nodes transmit whatever they like. Like we're posting forms onto the web, they would just post their data back to the server whenever they liked. But that was a little bit statistically variable. So actually we switched around to more of a controlled experiment where this PC gathered the data. So it's basically doing gets on each node, and each node would just say, here's some data. The other strange thing about this network is it appears to be up 24/7. So each node wakes up 8 times a second and just listens for the radio slightly. And if it hears any chitter-chatter, any packets at all, it then stays awake. So that means you can do very quick experiments. From your office, you can go and change the sampling rate on any node very easily, and so on and so on. Check the routes on them. So a very flexible system. So we investigated web pages because we thought it would be good to try web pages from a tiny microcontroller so that people could see, for example, a page that says, do you want to configure your sensors, or do you want to change the sampling rate, this kind of thing. And up here, of course, you can see these huge IP version 6 addresses. You will never know the address from memory again of your devices once you use IPv6. But this is what reminded us that HTTP, the standard web protocols, are not that efficient. The problem with web protocols is we're actually sending characters like G, E, T, space, slash, blah, 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 HTTP, one, carriage return, line feed, etc., in order to send a request. And then when it comes back to us, it's a nice human readable thing, which we've got used to, but it is too heavy for these very lightweight radio protocols that expect to have small packets. If you're sending lots of ASCII text that could just be 1 byte, there's something wrong. And in fact, the web itself is moving away from this web that we know. The web is moving in HTTP2 to a more binary form that we'll never be able to read again ourselves, but will make the web more efficient and cope with all our web requests, which we seem to do every split second. So this CoAP protocol is what's taking over for these kinds of devices, and it was built by an international community specifically to have a very lightweight, small packet. In a very small packet, you can send a GET request to a resource on the node itself, like /temperature or /average battery or something, and get 1 packet back very, very quick. And it has basically almost an interoperability with a web protocol, so you can actually map web requests to this as well if you wanted to. So it's tuned to this low power stuff, uses much less battery power, and you rely on using the techniques we already know. But then how do you send your data? You don't really want to suddenly use a beautifully efficient binary protocol for the main system and then send XML or some kind of ASCII tagged stuff. So we discovered that Google had already made a thing called protocol buffers so that they could send structured data around the networks. And in fact, there's a newer one, more standard, less Google-driven, which is also emerging. So this lets you do exactly what you would do in XML pretty much, where you send fields with their types, but it's packed into a tiny binary blob, And at the database end, when you pull it apart, you find temperature is afloat, accelerometer has 3 readings, all this kind of structure that you'd expect, which is great. Oh, I'm going backwards. So we actually use that to store the data and to transmit the data. CBOR is the new one if you're interested in looking it up. So what operating system do you use? Operating systems are a bit of an enabler. So we've seen the way that Linux, for example, is a massive enabler in the server community. And on this kind of level of hardware, there is no one operating system to help you. So wouldn't it be nice if there were some like de facto standards, but there aren't at the moment. So we use this thing which had emerged from some students in Stockholm University, which has quite a large following. And the key thing about this tiny operating system was not that it could run in tiny amounts of memory, but that it came with the TCP/IP stacks, the 6LoWPAN, IPv6 stacks, and someone had written a co-app library for it. So we could just then add our own protocol stuff on top of this to run our experiment. So this is what we ended up making. We always end up making our own hardware. So in this case, we tried not to, but we ended up, I think we had one board at one point from Texas Instruments with the radio chip on it. But basically, we had our one ARM core chip on here running Contiki, and then lots of power electronics to talk to the sensors. And we're using various techniques to make a sort of plug-and-play sensor. So very similar to the probe, you get various interfaces to various sensors, but we are trying to plug them all into RS-485, and that's the kind of thing that you will get if you buy an off-the-shelf sensor from someone in this exhibition hall. They'll say, do you want RS-485 or do you want some other semi-proprietary thing? Oh, so the key thing about this is that the radio is actually just 20 milliwatts, 25 milliwatts. So it's hundredths of the power of Wi-Fi, very low power, low speed. It's only like 20,000 bits per second, so that is low speed, but plenty with this environment. So we had some fun with the sensors. We actually designed some of our own sensors. So for example, we made these smart sensors that plug straight in and say what they have attached to them. And on the end, we put things like chains of accelerometers and temperatures sensors so that you could do profiles through soil, you could do profiles out across peat, and so on. And these sensors actually turned out to be quite a nice thing to play with because we could see what the manufacturers feel like when they make these plug-and-play, just plug it in and you'll get rainfall or humidity. We also made some very simple water depth sensors so that we could just measure stream depths in places where you wouldn't normally be able to afford to have a whole logger. And these little boxes just sat on the ground with their little antenna, and that was sufficient for them to mesh network across into the whole system. The nodes where we felt they should really be have a little bit more battery power because they're really routing lots of data through them, we actually gave them a small solar panel, we gave them a slightly better antenna, we gave them a little Davis Met Station tripod, just so that they were off the snow, just to protect them a little bit. And there were some areas where we had to learn from the peat specialists. For example, how do you walk on this peat bog without damaging it? You kind of put ladders out, etc. And how do you protect these wires from small animals? We didn't have small animals in Iceland. In Scotland, everything wants to eat your equipment. So here is a temperature profile across the peat. So literally putting fairly cheap one-wire temperature sensors where you want them, burying them, and then leaving it to take the measurements. Here is a wee lochen, a small pool of water that has frogs and wildlife and goes up and down a lot with a water stick, a rain gauge, and a few things like this. And this, unbelievably, talks the whole 3 kilometers down. For some reason, it likes to just talk off the edge of this cliff straight back 3 kilometers away without any assistance. And it's working right now, which is incredible. So the nice thing about doing all these projects is you get long-term data. By the time you've done version 1, 2, 3, and so on, you find, oh, we have 3 years of data of temperature on the top of the mountains, and so on. And we did actually get useful data from the peat profiles and from various sensors we thought were just experimental things to test the networking protocols. We did actually end up seeing some nice data which could be analyzed and published purely as earth science. So what we learned really was that it is possible to make these systems standards compliant, from the radio layer through to the IP layer, through to the CoAP kind of web layer. Everything above that is what people in this room are good at, all the data processing and the storage and the metadata, et cetera, so I'm not going to talk about that. But at least this provides a kind of view into maybe in the future we would expect Internet of Things style devices in the AGU companies that come and exhibit stuff. Maybe one day they'll say, our devices don't just have Wi-Fi, they can do this low-power stuff across your mountains, which would be very nice. Recently, I've kind of gone backtracking a little bit. So GPS is obviously a very, very important device for measuring flow of ice, because measuring the speed of ice with pinpoint accuracy is extremely important. Although with aerial imagery and satellite images, you can do coarse measurements. Having an actual GPS on a location you want to track is still basically the way people measure ice velocities. And so we had done this in the past in Iceland. We'd placed things like Leica GPS units, and the methodology is you leave one on a rock or somewhere fixed, you do recordings, you leave another one somewhere which is moving, you do recordings, you send 2 sets of recordings home for each reading, and then you post-process. So this could be 200K, 300K, 400K of data. Not the best thing to send over a low-power radio. But that's the way it's been done for many years. Most people actually just leave the data on the unit and go and collect it with a laptop, for good reason. However, with real-time kinematics, maybe we could do something that was slightly less accurate, but live, straight onto the internet. So we were fortunate enough, this just shows you the importance of mixing GPS with things like subglacial data. So you may have all your subglacial pressure changes, temperature changes, and so on, but when you suddenly bring in velocity changes from the surface, it starts to make sense. The glacier is moving, it's generating energy underneath, which is increasing the temperature. You can start to put the puzzle together even better. So GPS is very, very important. So we were lucky enough to get funding from Formula E, which is the electric version of Formula One. So they wanted to do a promo really for their sustainability unit, which shows the importance of electric vehicles in the future, autonomous vehicles, and so on. They wanted to do a promo video where it started off talking about climate change and had one of their cars driving on an iceberg initially in Greenland. They ended up actually driving a car on a Greenland ice, piece of ice that they'd polished a little bit on a glacier, not on an iceberg. However, we gave them a tracker and they put it on the iceberg, and it went all the way down the coast of Greenland, sending little Iridium messages. Very simple experiment. We had to do it in 1 week. But we managed to get some sponsorship from them to do some science. And what we did was we looked at the technologies that are coming out for quadcopters and UAVs, which are to make very accurate GPS recording live, so RTK, real-time mode, but for low weight, low energy, fairly low cost. So these things cost like $600 instead of $2,000, $3,000, and are designed really to go in a vehicle of some sort. But the accuracies are quite nice. So with traditional GPS, you might expect millimeter accuracies, almost more than you want. With these things, you expect 1 or 2 centimeter accuracies. However, if that's good enough, that will do a measurement for you very quickly, like 40, 50 seconds. So we talked to Swift in San Francisco, ironically, at the last AGU, and we were very impressed by the systems, and we actually put together, I went back to basics, and I thought, okay, we're not going to have complicated networking, we're really just testing the GPS units. I won't try to push every technology into this. We'll just use a tiny microcontroller and some very, very basic units to control the GPSs. So this is literally me experimenting in the garden, putting this thing together. And MicroPython turned out to be a lifesaver. So on this tiny microcontroller, you can just drop the Python file on it and run the Python, which is beautiful. Anyone who loves Python for server reasons, I now love Python for microcontroller reasons. And debugging your Python is a bit of a nightmare, but it looks beautiful and it's very easy. So it's easy to Google almost everything you want. And my code was only about 600 lines for the entire project of gathering GPS data, sending it out on Iridium, going to sleep, setting schedules, and so on. Very nice. So in the end, I ended up with more little Pelly boxes, except this time you had this little tiny weeny guy here. It's only like 2 centimeters long, running the MicroPython, a real-time clock chip to make sure that the schedule was exact. So I wanted the GPSs to wake up exactly on time together, take a reading, and then go back to sleep exactly together. So this is the GPS unit with its radio, because it needs to either transmit or receive corrections. And that is an Iridium unit you can buy for a few $100s, which for about 10 cents every 50 bytes you can send anywhere in the world. That would make it scalable to use in Greenland or Antarctica or anywhere you'd want to do these kinds of readings. So we went out to some of our they really don't like these videos, these systems. One of our favorite sites in Iceland, where you could walk up to the ice and choose 2 glaciers, contrasting glaciers, one which had a huge water body in front of it. So this is basically melted over a period of about a decade and left a lot of water, which actually accelerates the melting of the ice. But we could walk up to an area and deposit one on there, and the other side of this ice cap, there is a nice huge kilometer-wide piece of ice we put another tracker on. So this is what the trackers look like. The structure was actually inspired by someone from the Met Office in Reykjavik. And there's a little GPS antenna on here, a little box slung underneath it. It's basically kept off the ice because shadows make the ice appear to grow. So where there's not shadow, it melts, and where there's shadow, it appears to grow. It's kind of inverse melting logic. Anyway, these guys were left on the ice, and then on the moraine or somewhere fixed nearby, you had a similar system that would wake up and transmit radio corrections to the other one. And when the other one, after about 45, 50 seconds, gets a good lock, good fix, it would just turn off the GPS, turn on the Iridium thing once a day, send packets of messages out in horrible ASCII format. You don't want to know CSV. Oh. However, it made and is still making live data. And this is the key test of any of these systems. Do you end up with a useful stream of data? So this is from that glacier I showed you, Fjalsjökull, which is very fast moving, and you can actually see a plot here of it moving and accelerating here. The actual points are far enough apart that you can actually see it's accelerated here, and you can see that the temperature at the Met station in the valley was actually very high during that period, which led to a faster movement, and so on. So this is just since August, when it was installed. So the data comes in at 1 p.m. every day. You just get data coming into the database from the Iridium system, unpacked, and you can see your data every day, which is nice, but it's slightly annoying because you want to see it every day and you don't really have time to see it every day. So we tend to look at it like once a week, put the data together, see if anything interesting has happened, and then the data will just pile up the rest of the time. However, it's shown that it's worked. The other glacier, for example, is very slow moving. If you come to the poster tomorrow, you'll be able to see that data in detail. But it shows that with 2 centimeter accuracy, if you're measuring these kinds of things, it is actually good enough to get a fast reading and not turn on GPSs, burn lots of energy, produce lots of data that you need to transmit and post-process, and so on. So in summary, what we've learned and what we've done is we actually installed the first network for sensors sensor network in glaciers. No one's actually done a big system like that since. I can understand why. But using custom hardware, custom software, very bespoke systems, but it was the first system to produce wirelessly networked sensors from the bed of glaciers. We then produced the first IoT style, so fully IP, fully web compliant sensor network deployed to actually get real data. So most people would do that in their lab to measure the lab temperature or something like this, not necessarily go up a mountain and deploy this. So that showed us that you do expect a little bit of an overhead by using standards. It's not as beautifully perfect energy-wise or byte-wise as we would make from scratch, but it really does work, and it's worth paying the price to be able to talk to devices from Firefox from your office. It is incredible. And we've made the first web-connected real-time kinematic GPS tracker as well, which is kind of slightly stunning. And this is really because of those lower cost, smaller, quite easy to use real-time kinematic GPSs that have come out of the UAV, AUV world. And what we're doing now is, of course, to de-risk that project, we didn't give it any sense of its battery voltage or whether it was going to fail. It just basically, one day it will stop working. We don't know when. So it's a bit of a waiting game, but de-risking it meant basically not putting any other sensors in there, which is a good strategy, obviously, because it worked. So finally, you don't do these projects just with technology. Over the years, we've been very fortunate to work with brilliant students, collaborators. You need people who can do the GIS, who can set the scene for what's the fundamental earth science you actually want to gather. You need people who are good at electronics, who can build circuits, test and debug, computing people. You need keen students who work at 3 in the morning to finish that one bug in the hut out in Iceland on the last day to get the things working, and so on and so on. We also sneak in our kids who carry stuff around, but that's another story. And I've managed to give you some time for questions. Thank you.
Does anyone have any questions for Professor Martinez?
Really a fascinating talk and really fun. One of the things that you mentioned sort of throughout the talk was the importance of standards in this work in many different phases. I'm wondering if your experience with those standards is working into things like Sensor ML or Internet of Things APIs or things, some of the standards sort of related to sensor webs that are being developed by the OGC.
Yes, so at the moment we're working with the W3C on a thing called Web of Things, because that's really seeing the IoT systems as a piece of web architecture. However, that won't actually do what we need in Earth science quite so much. It will boost things like devices in the home a lot, but I think that the low power type area that we're working in actually drives us towards the parallel world of CoAP, but on similar stacks. So although you can buy light bulbs that use exactly the same tech and standards, they will tend to use things like 2.4 gigahertz radios and so on. In terms of things like sensor ML, that layer of stuff at the lower end has been very neglected, and more work is needed.
Thanks.
So I have two almost completely unrelated questions. Question number one, I'm very impressed with the architectures that you created, infrastructure of these low-cost sensors. However, one of the advantages of commercial sensors is high accuracy and calibration. And do you have any problems with your sensors drifting away from the calibration? And if you do, how do you compensate for that? That's question number one. Question number two, recent years, these smart home sensors become very cheap and very available. And like, for example, you can get a Samsung smart home array of 10 sensors for like under $100, right? Have you looked into using any of that for any of your projects?
Okay, so on the calibration, yes. Initially in Iceland, we were putting, the question was, how do you cope with the calibration of all these sensors? Because some of the sensors we make ourselves from things we drop in, so you just buy a pressure sensor, buy a temperature sensor. But of course you need the whole provenance chain to really store what the accuracy, what the deployment of the sensor was, and so on. In the bad old days, that would all be handwritten notes that would go on the system separately as metadata. It is now slightly more possible. On these systems in Scotland, you can actually ask, what are your resources? And so you could get back a list of URIs, and one of them could be my sensor metadata. So you could get that once, and you could get a nice list of URIs that went off to Honeywell, to the pressure sensor, went off to something else that explained something about the sensors. So you could actually embed that knowledge into the systems, which would be very nice. You would then have self-organized metadata from some aspects, which would be quite cool. Second question was, oh yeah, so you can now buy things like Samsung and Apple Home Hub type things, which will link to your light bulbs and your fridge and so on. But we don't have that level of commercially available stuff yet for this, this low power, low frequency stuff. So we're really relying on some companies out there going for it and attempting to sell this stuff and persuading the rest of the community to join in. So that's a much harder task than, for example, Wi-Fi, people selling Wi-Fi chipsets to Samsung so that your device has Wi-Fi, and Amazon Alexa uses Wi-Fi, etc. It's much easier to get into that market and sell millions of them than it is to sell to earth science people. However, the earth science community does spend on very expensive equipment, so you'd imagine that it is possible, but someone needs to go and do it. It's quite difficult to persuade the manufacturers to jump and maybe risk their product line. So I'd say that was that's the main issue. Hi.
So we have another question?
Yeah, so I was wondering more on the physical side of things. What do you guys do for testing, putting them out in these really harsh environments? Is it just a lot of bathtubs and a lot of graduate students, or are there like other things that you do?
Did you mean for testing?
Yeah, like
Oh,
testing,
yeah. Okay.
yeah.
So this is how do we test these things? We're lucky in Southampton we have an oceanography department that has a deep pressure system. So we tested the pressure water resistance just by putting them into those massive tanks. And then the guy would say, do you want 2,000 meters or 3,000 meters? And we'd say, 200 or 300 meters, just a little bit, please, don't crush them. And we'd do the test there. For things like in engineering, similarly, we have these big cases where you could get down to, say, -3, and then put a known number of newtons on the side, kind of stress test type things. And that was the only easy way of calibrating the stress. Temperature, we did actually not calibrate our temperature. We made a ±5 centigrade, really accurate temperature sensor for the ice, because we were just buying ±30 degrees type sensors. We built a nice one, didn't have time to calibrate it, got all the way to Iceland, thought, oh dear, how do we calibrate something that's ±5? Bought some antifreeze, put it in the freezer, got it down to -20, and then I just sat in the kitchen with a hand meter writing down into Excel the whole calibration curve. It took hours and hours and hours. It actually turns out very difficult to warm up antifreeze. So yeah, should have thought ahead really.
Okay, thank you very much. And thank you for some really interesting questions as well. So, sorry, boss has told me off. So I'd like to thank Professor Martinez for a really interesting and entertaining talk today. I know it's very tough to actually write one of these lectures and to actually sort of give a real flavor for a whole career of effort. So I think it's appropriate that we thank Professor Martinez in the usual way for his lecture today. So, and I will jump down from here because I left the award down here. So there is an award. So, as well as the lecture, there is indeed an award which I would like to present you with. So, thank you very much. We'll come down there is a certificate, we'll give you that in a moment as well, so you don't have to wrestle them both. Yeah, we were going to come down and do a photo op, so, but anyway, thank you so much, and thank you for all of you for coming. The one thing I do want to mention before you run away is, if you found Professor Martinez's lecture really interesting today and you have an interest in sensor networks, there is actually a poster session tomorrow morning. I think you have a poster in that session that covers some of this work in more depth. So if you have an interest, please do go along and take the opportunity to perhaps talk to Kirk and ask him some more questions about this really fascinating work that he's been doing. So thank you very much. The other thing I will remind you about, while I think of it, there is the Ignite session this evening. at 6 o'clock. In the aquarium, which is just down the river walk, I think that it actually starts at 6:30, but the doors open at 6 o'clock. So if you'd like to go along and hear some really interesting small talks given by some of the people you probably already know, then please do go to that as well this evening. Union? Oh, did I forget that? Yeah. Remind me, what is the union tomorrow?
On how safe is our science.
Yes, there is a union session tomorrow. I'm being prompted here from the side, which is called How Safe is Our Science?
How safe and persistent.
Oh, how safe and persistent is our science. And where is that, Leslie? E2. E2. So again, if you want to come along to that, that's another session where we'll be addressing a whole raft of issues around informatics. But for now, thank you very much.